For nearly a century, we've told ourselves a story that everything, every star, every galaxy, every atom in your body emerged from a single point 13.8 billion years ago. But what if the Big Bang wasn't the beginning? What if it was just one event in an infinite cosmic story that stretches eternally into the past? Today's most advanced telescopes and brilliant theoretical physicists are uncovering evidence that our universe might be far stranger and more eternal than we ever imagined. From quantum loops that bounce through time to parallel universes colliding in higher dimensions, we're about to explore mind-bending possibilities that could rewrite the story of existence itself. If you're fascinated by the deepest mysteries of existence and want to explore more cosmic revelations, make sure to subscribe to this channel and give a thumbs up. Now let's begin. The Big Bang Theory, as we understand it today, began taking shape in the 1920s when Edwin Hubble noticed something peculiar through his telescope at Mount Wilson Observatory. Galaxies were racing away from us, and the farther they were, the faster they fled. This discovery, combined with Einstein's general relativity, led to an extraordinary conclusion: the universe is expanding. If we reverse this cosmic movie, everything converges to a single point of infinite density and temperature, what we call the Big Bang. But here's where things get interesting. The standard Big Bang model has always had a glaring problem. It can't actually describe the very beginning. When physicists try to push their equations all the way back to time zero, the math breaks down. Density becomes infinite, temperature becomes infinite, the laws of physics themselves cease to function. This singularity isn't just a place where strange things happen, it's where our understanding completely fails. It's like trying to divide by zero. The universe gives us an error message. In 1964, two radio astronomers named Arno Penzias and Robert Wilson stumbled upon something that would win them the Nobel Prize. While trying to eliminate noise from their antenna, they discovered a faint microwave signal coming from every direction in the sky. This was the cosmic microwave background radiation, the afterglow of the Big Bang itself, cooled by 13.8 billion years of cosmic expansion to just 2.7 degrees above absolute zero. The CMB became our baby picture of the universe, captured when it was only 380,000 years old. But as our instruments grew more sophisticated, this baby picture began revealing puzzles that the standard Big Bang couldn't explain. The Cosmic Background Explorer satellite, launched in 1989, showed that the CMB temperature is uniform to an extraordinary degree, varying by only 1 part in 100,000. This uniformity is deeply mysterious. Regions of space separated by billions of light-years have exactly the same temperature, even though they've never been in contact. It's like finding that everyone on Earth decided to wear the same outfit on the same day without any communication. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, made these measurements even more precise. It revealed that our universe is geometrically flat to an accuracy of 0.4%. This flatness is another cosmic coincidence that seems almost impossible. If the universe's density had been even slightly different 1 second after the Big Bang, different by 1 part in 10 to the 60th power, the universe would have either collapsed immediately or expanded so fast that galaxies could never form. These problems led physicist Alan Guth to propose cosmic inflation in 1980. According to inflation theory, the universe underwent a period of exponential expansion in its first fraction of a second, growing by a factor of at least 10 to the 26 in about 10 to the negative 32 seconds. This rapid expansion would smooth out any irregularities and explain the universe's flatness and uniformity. But inflation raises its own profound questions. What caused it? What came before it? And most mysteriously, if inflation happened once, could it happen again? or might it be happening all the time? Enter the concept of eternal inflation, developed by physicists like Andrei Linde and Alexander Vilenkin in the 1980s. In this scenario, inflation never completely stops. Most of space continues inflating forever, with only small regions dropping out of inflation to form pocket universes like our own. Our Big Bang wasn't the beginning of everything, it was just the beginning of our particular cosmic bubble. Beyond our universe lies an eternally inflating multiverse, constantly spawning new universes like bubbles in an infinite champagne bottle. The Planck satellite, launched by the European Space Agency in 2009, has given us the most detailed map of the cosmic microwave background ever created. Its data confirms inflation's predictions with remarkable accuracy, but it also revealed something unexpected: anomalies that might be evidence of physics beyond the Big Bang. There's a mysterious cold spot in the CMB that shouldn't exist, and subtle patterns that some physicists interpret as evidence of collisions with other universes, bruises from our bubble universe bumping into neighboring bubbles in the infinite multiverse. Roger Penrose, who won the Nobel Prize in Physics in 2020, has proposed an even more radical idea called Conformal Cyclic Cosmology. In his model, what we call the Big Bang was actually a transition from a previous universe that had reached its ultimate fate. After trillions upon trillions of years, when all black holes have evaporated through Hawking radiation and the universe contains nothing but photons, the distinction between large and small becomes meaningless. This infinitely large, cold, empty future universe becomes mathematically identical to the hot, dense beginning of a new Big Bang. Penrose claims to have found evidence for his cyclic model in the CMB itself. He and his collaborators have identified what they call Hawking points, spots in the cosmic microwave background that might be the echoes of black holes evaporating in the previous universe. These would be regions where enormous amounts of energy were released in the dying moments of the last cosmic cycle, leaving imprints that survived through the transition into our current universe. While controversial and disputed by many cosmologists, these patterns remind us that the Big Bang might not be the impenetrable barrier to the past that we once thought. Speaking of cosmic patterns and cycles, if you're curious about another fundamental mystery of the universe, check out my video, Why is Everything in the Universe Spinning?, where we explore the incredible fact that rotation seems to be a universal principle from subatomic particles to galaxy clusters. The link is in the description and pinned on the comments. Now let's dive deeper into what might have come before our cosmic beginning. Loop quantum gravity, one of the leading candidates for a theory of quantum gravity, offers another fascinating possibility: the Big Bounce. According to this theory, space itself is quantized at the smallest scales, made of discrete loops rather than being smooth and continuous. When you apply loop quantum gravity to the early universe, something remarkable happens. Instead of reaching infinite density at the Big Bang, the universe reaches a maximum density, about 10 to the 96th grams per cubic centimeter, and then bounces back, expanding again. Our Big Bang was actually a big bounce from a previous universe that had been contracting. Martin Bojewald at Penn State University has developed mathematical models showing how information from the previous universe might survive through the bounce. While most details would be erased by the extreme conditions, some features, like the overall size of the universe or certain quantum properties, might pass through. We could be living in a universe that carries fossil imprints from its previous incarnation, encoded in subtle patterns we haven't yet learned to read. The Ekpyrotic model, developed by Neil Turok, Paul Steinhardt, and others, proposes yet another alternative. Drawing from string theory, this model suggests our universe exists on a three-dimensional membrane, or brane. floating in a higher dimensional space. The Big Bang occurred when our brane collided with another parallel brane, converting the kinetic energy of the collision into the heat and matter of our universe. In this scenario, these collisions happen cyclically, with the branes separating and colliding again every trillion years or so. What makes the Ekpyrotic model particularly intriguing is that it solves many of the same problems as inflation, but through a completely different mechanism. The collision between branes naturally produces the flat, uniform universe we observe without requiring a period of exponential expansion. The Laser Interferometer, Gravitational Wave Observatory, or LIGO, might eventually be able to test this model by detecting gravitational waves from the brane collision, ripples in space-time that would have a distinctly different signature than those predicted by inflation. String theory itself opens up even more exotic possibilities. In string theory, what we perceive as particles are actually tiny vibrating strings in a universe with 10 or 11 dimensions. The extra dimensions are compactified, curled up so small we can't detect them directly, but these hidden dimensions might hold the key to understanding what came before the Big Bang. Some string theorists propose that the Big Bang was a transition where these extra dimensions suddenly changed their configuration, like a cosmic phase transition that reset the properties of our universe. The James Webb Space Telescope, launched in 2021, is revolutionizing our understanding of the early universe. It's discovering galaxies that formed much earlier than we thought possible, massive, mature galaxies existing just a few 100 million years after the Big Bang. These observations are forcing us to reconsider how quickly structure formed in the universe, and some cosmologists argue they might even challenge our understanding of the Big Bang itself. If galaxies formed too quickly, perhaps the universe is older than we think, or perhaps there was more structure already present at the moment of the Big Bang than our models predict. Black hole cosmology presents another mind-bending possibility. Some physicists, including Lee Smolin, have proposed that every black hole creates a new universe inside itself. When matter collapses into a black hole, it might not crush into a singularity, but instead bounce and expand into a new space-time region disconnected from the parent universe. Our entire universe might exist inside a black hole in another universe, and every black hole in our universe might contain baby universes of their own. This creates an infinite nested hierarchy of universes, each born from black holes in the previous generation. This idea has a fascinating implication for the laws of physics. Universes that produce many black holes would have more offspring universes. Over cosmic time, this would lead to a kind of natural selection, with the multiverse dominated by universes whose physical laws are optimized for black hole production. Intriguingly, the conditions that favor black holes, like the right balance of forces and particle masses, also tend to favor the formation of stars, planets, and potentially life. The quantum vacuum itself might hold clues to what preceded the Big Bang. Even in completely empty space, quantum mechanics tells us that virtual particles constantly pop into existence and annihilate. This quantum foam exists at scales trillions of times smaller than atoms, where space and time themselves become fuzzy and uncertain. Some theorists propose that our Big Bang was simply a particularly large quantum fluctuation, a random bubble that grew large enough to become a universe. In this view, Big Bangs might be happening all the time at quantum scales, but only rarely do they grow large enough to create universes like ours. The notion of time itself becomes profoundly strange when we consider what might have existed before the Big Bang. Stephen Hawking, together with James Hartler, proposed the no-boundary proposal in 1983. In their model, as you go back toward the Big Bang, time gradually becomes more like space. There's no sharp beginning, no first moment. Instead, time smoothly rounds off like the South Pole on Earth. Asking what came before the Big Bang becomes like asking what's south of the South Pole. The question itself doesn't make sense because the very concepts of before and time cease to apply. This idea emerges from applying quantum mechanics to the entire universe, what physicists call quantum cosmology. In classical physics, the universe must have a definite history, but quantum mechanics suggests the universe might exist in a superposition of all possible histories. The wave function of the universe, as Hawking called it, describes all possible ways the universe could have emerged from nothing. We observe one particular history, not because it's the only one, but because it's the one compatible with our existence. Recent observations from the Atacama Cosmology telescope in Chile have provided new ways to test these exotic ideas. By measuring the polarization of the cosmic microwave background with unprecedented precision, scientists can look for signatures of physics beyond the standard Big Bang model. They've found hints of what might be primordial gravitational waves, ripples in space-time from the universe's earliest moments, but also anomalies that don't fit neatly into any current model. The Dark Energy Survey, using the Blanco telescope at Cerro Tololo in Chile, has mapped hundreds of millions of galaxies to understand the universe's expansion history. Their data reveals that dark energy, the mysterious force accelerating cosmic expansion, makes up about 68% of the universe's energy. But here's the profound implication. If dark energy remains constant or increases over time, our universe will expand forever, eventually reaching a cold, empty state. This fate might not be the end, but a transition to the next cycle, as Penrose suggests, or the birthing ground for new quantum fluctuations that spawn future universes. The concept of the multiverse radically reframes what we mean by beginning. Max Tegmark at MIT has classified different levels of multiverse, from regions beyond our observable universe to quantum parallel worlds to universes with entirely different mathematical structures. At the highest level, every mathematically possible universe exists. Our Big Bang wasn't the beginning of existence, it was just the beginning of our particular mathematical structure. Somewhere in this infinite ensemble, there are universes with different numbers of dimensions, different physical laws, perhaps even different types of mathematics. String theory's landscape presents an almost incomprehensible vision of possibility. The theory predicts 10 to the 500 different ways to compactify the extra dimensions, each giving rise to a universe with different physical properties. Leonard Susskind and others argue that eternal inflation naturally explores this vast landscape, creating pocket universes with every possible configuration. Our universe, with its particular set of physical constants that allow for stars, planets, and life, is just one random valley in an infinite mountain range of possibilities. The anthropic principle takes on new meaning in this context. We observe a universe compatible with our existence, not because it was designed for us, but because we couldn't exist in the vast majority of other universes. It's the ultimate selection effect. We can only find ourselves in a universe that permits observers. The precise values of physical constants that seem so finely tuned, like the strength of gravity or the mass of the electron, are just local accidents in our particular cosmic bubble. BICEP, a series of telescopes at the South Pole, searches for primordial gravitational waves by measuring subtle patterns in the CMB's polarization. In 2014, BICEP-2 announced they'd found evidence of these waves, which would have been strong confirmation of inflation. However, further analysis revealed the signal was contaminated by dust in our own galaxy. This reminder of how difficult these observations are also highlights how actively scientists are searching for evidence of what preceded or caused the Big Bang. The Large Hadron Collider at CERN provides another window into the early universe. By colliding particles at energies approaching those of the first microseconds after the Big Bang, physicists can study the fundamental forces under extreme conditions. They've discovered the Higgs boson, confirming how particles acquire mass, but they've also found that the Higgs field might be metastable. Our universe could be in a false vacuum state that might eventually decay, triggering a new Big Bang that would destroy everything and create a new universe with different physics. Cosmological natural selection, proposed by Lee Smolin, suggests an evolutionary process operating across universes. If universes reproduce through black holes and inherit slightly modified physics from their parents, then over time the multiverse becomes dominated by universes good at making black holes. This process requires no designer, just the simple principle that universes that reproduce more successfully become more common. Our universe's apparent fine-tuning for black hole production, and coincidentally for life, might be the result of countless generations of cosmic evolution. The measurement problem in quantum mechanics, how quantum possibilities become classical realities, might be connected to cosmology's deepest questions. Some physicists propose that consciousness or observation plays a fundamental role in creating reality. If so, the universe might require observers to exist, creating a strange loop where the universe creates conscious beings who then retroactively collapse the universal wave function, bringing the universe into existence. John Wheeler called this the participatory anthropic principle. We're not just observers, but participants in creating cosmic history. The arrow of time presents one of the deepest puzzles when contemplating what came before the Big Bang. We experience time flowing from past to future because entropy, disorder, always increases. But the early universe was in an incredibly low entropy state, with matter and energy distributed almost perfectly uniformly. This is staggeringly improbable, like dropping a glass and having it spontaneously assemble rather than shatter. Sean Carroll at Caltech proposes that our Big Bang might have been a fluctuation from a much larger multiverse in thermal equilibrium, where time has no preferred direction, and Big Bangs spontaneously occur in both temporal directions. The holographic principle, first proposed by Gerard 't Hooft and refined by Leonard Susskind, suggests that all the information in our three-dimensional universe might be encoded on a two-dimensional surface, like a hologram. This isn't just abstract mathematics, it's been confirmed for certain spacetimes through the ADS-CFT correspondence. If our universe is fundamentally holographic, then the Big Bang might have been a transition from a lower dimensional to a higher dimensional description of the same information. Reality itself might be more fluid and transformable than we imagine. Observations from the Sloan Digital Sky Survey have mapped the large-scale structure of our universe in unprecedented detail, revealing vast cosmic voids and filaments of galaxies stretching billions of light-years. Some cosmologists see patterns in these structures that might be remnants from before the Big Bang. The distribution of galaxy clusters shows slight preferences for certain scales and orientations that don't perfectly match inflation's predictions. Could these be fossilized imprints from a previous cosmic epoch? The black hole information paradox, which Stephen Hawking worked on until his death in 2018, connects to questions about the universe's beginning. If information can't be destroyed as quantum mechanics demands, then what happens to information that falls into a black hole? Hawking eventually conceded that information must somehow escape, possibly encoded in subtle correlations in Hawking radiation. If our universe emerged from a black hole or a similar singular event, information from the previous universe might be similarly encoded in subtle patterns we're only beginning to detect. Variable speed of light cosmology, proposed by João Magalhães and Andreas Albrecht, offers a radical alternative to inflation. Instead of space expanding exponentially, they suggest the speed of light was much higher in the early universe. This would allow different regions to communicate and reach thermal equilibrium without inflation. While controversial, This theory makes testable predictions about patterns in the cosmic microwave background that future observations might confirm or refute. The Euclid Space Telescope, launched by the European Space Agency in 2023, is mapping billions of galaxies to understand dark energy and test our cosmological models. Its observations might reveal whether dark energy is truly constant or changes over time. If dark energy varies, it could be a field that cycles through different values, potentially triggering transitions between different cosmic epochs. We might be living in just one phase of an eternally oscillating universe. Causal set theory proposes that space-time isn't continuous but made of discrete points connected by causal relationships. In this framework, the Big Bang might have been a phase transition where the causal structure of space-time suddenly changed, like water freezing into ice. Raphael Sorkin and others have shown that this discrete structure naturally produces the observed value of dark energy, suggesting a deep connection between the microscopic structure of space-time and cosmology. The trans-Planckian problem challenges inflation itself. During inflation, quantum fluctuations that seed cosmic structure would have started smaller than the Planck length, the scale where quantum gravity dominates. We don't know what physics operates at these scales, so inflation's predictions might be unreliable. This ignorance about trans-Planckian physics might hide clues about what preceded or triggered inflation. Observations of quasars, supermassive black holes feeding on gas in distant galaxies, provide another window into the early universe. The Subaru telescope in Hawaii has discovered quasars that existed when the universe was less than 700 million years old. These billion solar mass black holes formed surprisingly quickly after the Big Bang, suggesting either exotic formation mechanisms or that some structure might have survived from a previous cosmic epoch. The concept of time crystals, confirmed to exist in 2017, shows that matter can exhibit temporal periodicity, just as normal crystals show spatial periodicity. Frank Wilczek, who proposed the idea, has suggested that the universe itself might be a kind of time crystal, cycling through states eternally. The Big Bang might be just one phase in this cosmic time crystal's eternal oscillation. Quantum entanglement might connect our universe to what came before. In quantum mechanics, entangled particles remain connected regardless of distance. If our universe emerged from a quantum event, it might remain entangled with whatever preceded it. This quantum connection could, in principle, carry information from before the Big Bang, encoded in correlations too subtle for our current instruments to detect. The JWST has discovered galaxies that challenge our models of early cosmic evolution. Some galaxies observed at redshift 20, just 300 million years after the Big Bang, are unexpectedly massive and mature. These observations have led some cosmologists to propose that the universe might be older than we think, or that some galactic seeds might have originated before our Big Bang, surviving from a previous cosmic cycle. Primordial black holes, if they exist, would be relics from the universe's first moments. Unlike stellar black holes formed from dying stars, these would have formed from extreme density fluctuations in the early universe. The LIGO and Virgo gravitational wave detectors search for mergers of such black holes. If found with the right mass distribution, they might carry information about physics at, or even before the Big Bang. The cosmic neutrino background offers another potential window into the universe's deepest past. These ghostly particles decoupled from matter just 1 second after the Big Bang, even earlier than the cosmic microwave background. While we haven't directly detected this neutrino background yet, experiments like Ptolemy are being designed to catch these ancient messengers. If successful, they would give us information from when the universe was at temperatures of 10 billion degrees, potentially revealing physics that preceded our current cosmic epoch. Loop quantum cosmology makes specific predictions about the universe's maximum density, about 10 to the 96th grams per cubic centimeter, the Planck density. Above this density, quantum geometry effects cause gravity to become repulsive rather than attractive. This repulsive gravity would cause any collapsing universe to bounce rather than form a singularity. Abhay Ashtekar at Penn State has calculated that some information from the previous universe could survive through this bounce, particularly the total volume of space and certain geometric properties. The Wheeler-DeWitt equation, sometimes called the wave function of the universe, attempts to describe the entire cosmos quantum mechanically. This equation has no time variable. Instead, time emerges from the correlations between different parts of the universe. In this framework, the universe doesn't evolve through time. Rather, time is an emergent property of the universe's quantum state. The Big Bang wasn't an event in time, but the boundary where our notion of time begins to make sense. Dark flow, discovered in 2008, is a mysterious motion of galaxy clusters toward a particular region of sky. This uniform flow extends at least 2.5 billion light-years and can't be explained by any structures within our observable universe. Some cosmologists speculate it might be caused by structures beyond our cosmic horizon, possibly remnants from before inflation, or the gravitational pull of another universe entirely. NASA's Planck satellite data has been scrutinized for confirmation of this flow, with debates continuing about its reality and implications. The axis of evil, despite its dramatic name, is a serious cosmological puzzle. WMAP and Planck data show that the largest temperature fluctuations in the CMB seem aligned with our solar system's plane. This is deeply weird. The CMB should look the same from any vantage point. Some physicists propose this alignment might be evidence that our universe has a fundamentally different geometry than we assume, perhaps inheriting a preferred direction from whatever preceded the Big Bang. Conformal cyclic cosmology predicts specific patterns in the CMB that Penrose calls Hawking points. These would appear as rings of slightly elevated temperature, remnants of the explosive evaporation of supermassive black holes in the previous cosmic aeon. While Penrose's team claims to have found such signals, other cosmologists argue these patterns could arise from random noise. The debate highlights how difficult it is to extract information about pre-Big Bang physics from current observations. The multiverse interpretation of quantum mechanics proposed by Hugh Everett suggests every quantum event branches reality. Applied to cosmology, this means the Big Bang might have created not one universe, but an infinite ensemble of parallel universes, each with slightly different initial conditions. We observe this particular universe simply because we're in it. Other versions of us in parallel branches observe different cosmic histories. The Big Bang wasn't a unique event, but an infinite proliferation of universes. Brane world scenarios from string theory suggest our universe exists on a three-dimensional surface in a higher dimensional space. Gravity, unlike other forces, can leak into these extra dimensions. This could explain why gravity is so much weaker than other forces. It's diluted across dimensions we can't see. Lisa Randall at Harvard has shown that these models make testable predictions about gravitational wave propagation that future detectors might verify. The measure problem in eternal inflation is a profound challenge. If inflation creates infinite pocket universes, how do you calculate probabilities? Everything that can happen does happen infinitely often. This makes it nearly impossible to make predictions or test the theory. Some cosmologists see this as evidence that eternal inflation, despite its elegance, might be fundamentally flawed or incomplete. Observations of the cosmic web, the largest structure in the universe, reveal that galaxies are distributed along filaments with vast voids between them. Some cosmologists propose these patterns might be inherited from before the Big Bang. If the universe underwent a bounce or emerged from a previous aeon, density fluctuations from that earlier epoch might have seeded the structures we see today. The lithium problem highlights gaps in our understanding of the early universe. Big Bang nucleosynthesis predicts how much of each light element should have formed in the first few minutes. The predictions match observations perfectly for hydrogen and helium, but there's 3 times less lithium-7 than expected. This discrepancy might point to new physics operating in the early universe or even processes that preceded the Big Bang. Analog gravity experiments use laboratory systems to simulate cosmic phenomena. Researchers have created acoustic black holes in flowing fluids and observed Hawking radiation. These experiments suggest that key features of cosmology might be emergent rather than fundamental. If gravity and space-time can emerge from more basic constituents, then the Big Bang might have been an emergence event rather than a creation event. The entanglement structure of space itself might hold clues about the universe's origin. Recent work in quantum gravity suggests space might be woven from quantum entanglement. Changes in entanglement patterns could cause space to expand, contract, or even tear. The Big Bang might have been a sudden change in the universe's entanglement structure, transitioning from one spatial configuration to another. The discovery of time asymmetric processes in particle physics adds another layer to the mystery. While most physical laws work the same forwards and backwards in time, certain rare kaon and B meson decays show a slight preference for one time direction. This CP violation is tiny, but might be connected to why our universe contains matter rather than antimatter. If time itself can distinguish between past and future at the quantum level, perhaps the Big Bang was a moment when the universe chose its arrow of time from a more symmetric predecessor state. Gravitational wave astronomy, revolutionized by LIGO's first detection in 2015, might eventually reveal echoes from before the Big Bang. Some theorists predict that if our universe bounced from a previous contracting phase, gravitational waves from that earlier epoch might have survived the bounce. These primordial gravitational waves would have a distinct spectrum different from those produced during inflation. Advanced LIGO and future space-based detectors, like LISA, might detect these ancient ripples. The swampland conjectures in string theory suggest that most seemingly consistent theories of quantum gravity are actually impossible. They live in the swampland rather than the landscape of valid theories. This severely constrains what kinds of universes can exist and how they can transition from one to another. The Big Bang might have been one of the few allowed transitions between viable universes, selected not by chance, but by the mathematical consistency of quantum gravity. Observations of ultra-high energy cosmic rays pose puzzles for standard cosmology. The Pierre Auger Observatory in Argentina detects particles with energies that shouldn't be possible. They should lose energy through interactions with the CMB before reaching Earth. Some physicists speculate these particles might be relics from the Big Bang itself, or even messengers from a previous universe, carrying information across the cosmic transition. The Hubble tension, the disagreement between different measurements of the universe's expansion rate, has become one of cosmology's most pressing problems. Measurements using the CMB give one value, while observations of nearby supernovae give another, higher value. This discrepancy might indicate that we're missing something fundamental about cosmic history. Perhaps the universe's expansion has been more complex than we thought, with transitions or phases that connect to pre-Big Bang physics. Quantum tunneling could have triggered the Big Bang. In quantum mechanics, systems can tunnel through barriers to lower energy states. The universe might have tunneled from a previous metastable state to our current one, with the tunneling event appearing as the Big Bang. This process, called false vacuum decay, could happen again, ending our universe and beginning another. we might be living in just one episode of an eternal sequence of tunneling transitions. The cosmic no-hair theorem suggests that inflation erases almost all information about what came before. Like a cosmic reset button, inflation would smooth away any irregularities, erase any structures, and leave us with a nearly blank slate. But nearly is crucial. Some information might survive in subtle ways we're only beginning to understand. The challenge is learning to read these faint cosmic fossils. Studies of the universe's topology, its overall shape and connectivity, could reveal pre-Big Bang influences. While locally the universe appears flat, it could be globally curved or have a non-trivial topology like a torus or Klein bottle. The compact collaboration searches for patterns in the CMB that would reveal such exotic topologies. A universe with unusual topology might be evidence of special initial conditions inherited from whatever preceded the Big Bang. The emergent space-time paradigm suggests that space and time themselves arise from something more fundamental. In approaches like entropic gravity or the ADS-CFT correspondence, space-time geometry emerges from quantum information. The Big Bang might not have created space-time, but rather marked a transition in how quantum information organizes itself into the space-time we experience. Reality itself might be more like a computation or information process than a physical entity. Observations of baryon acoustic oscillations, frozen sound waves from the early universe, provide a cosmic ruler for measuring distances. The dark energy spectroscopic instrument is mapping millions of galaxies to trace these oscillations with unprecedented precision. Deviations from expected patterns might reveal influences from before the Big Bang or indicate that our cosmic history is more complex than the standard model suggests. The magnetic monopole problem asks why we've never detected these particles that many theories predict should exist. Inflation provides one answer. It diluted any monopoles to undetectable levels. But if monopoles don't exist because something prevented their formation, that something might have occurred before or during the Big Bang. The absence of monopoles might be a clue about the universe's initial conditions or formation mechanism. Cosmic variance, the fundamental statistical uncertainty in cosmological observations, limits what we can learn about the universe's largest scales. We only have one universe to observe, so we can't distinguish between genuine features and statistical fluctuations. This cosmic variance might hide evidence of pre-Big Bang physics in patterns we dismiss as random noise. Advanced statistical techniques and observations of the universe at different times might help overcome this limitation. The quantum Zeno effect shows that frequent observation can freeze a quantum system's evolution. Applied to cosmology, this suggests that the universe's quantum state might be stabilized by internal observers. We're not passive witnesses to cosmic history, but active participants whose observations might influence how the universe evolves. The emergence of observers might have been a crucial transition that stabilized our universe's properties after the Big Bang. The bootstrap paradox in cosmology presents a mind-bending possibility. If closed, time-like curves exist, paths through space-time that loop back to their own past, then information could exist without origin. The universe's initial conditions might be self-consistently determined by their own future evolution. The Big Bang's properties might have been selected not by prior causes, but by the requirement of consistency with the universe's entire future history. This isn't causation as we normally understand it, but a kind of cosmic self-consistency principle. Recent analysis of the BOSS survey, baryon oscillation, spectroscopic survey, has mapped the universe's expansion history over the past 6 billion years with remarkable precision. The data shows that dark energy's strength has remained mysteriously constant even as the universe expanded by a factor of 2. This consistency is puzzling because most fields in physics change as space expands. If dark energy is truly constant, it might be a property of space-time itself rather than a field, possibly inherited from whatever process created space and time. The firewall paradox, proposed in 2012, suggests that black hole event horizons might be surrounded by high-energy firewalls that incinerate anything falling in. If our universe emerged from a black hole or similar singular event, we might have passed through such a firewall. The information scrambling that occurs at firewalls could explain why we can't access information from before the Big Bang. It's been thermalized beyond recognition. Observations of the Lyman alpha forest, absorption lines from intergalactic hydrogen clouds, let us map the universe's structure at different cosmic epochs. Some patterns in this forest are difficult to explain with standard inflation models. They might be fossils from before the Big Bang, structures that somehow survived the cosmic transition. The upcoming extremely large telescope will map the Lyman alpha forest with unprecedented detail, potentially revealing more such anomalies. The vacuum catastrophe, the 120 order of magnitude discrepancy between the predicted and observed vacuum energy, might hint at pre-Big Bang physics. Why is the vacuum energy so incredibly small but not zero? One possibility is that it's a residue from a previous cosmic epoch, diluted by inflation but not completely erased. Understanding the vacuum energy might require understanding the universe's entire history, including what came before. Cosmic strings, if they exist, would be one-dimensional defects in space-time left over from phase transitions in the early universe. They would be thinner than a proton but potentially light-years long, with enormous gravitational effects. No cosmic strings have been definitively detected, but if found, they might carry information from the universe's earliest moments, or even before. The nanograv pulsar timing array searches for gravitational wave signatures of cosmic strings. The many worlds interpretation of quantum mechanics, when applied to quantum cosmology, suggests that the Big Bang created not one universe, but an infinite branching tree of parallel realities. Each quantum event spawns new branches, creating an ever-growing multiverse. What we call the Big Bang might be the point where this branching began, emerging from a simpler pre-quantum state. Every possible version of cosmic history exists somewhere in this quantum multiverse. Studies of primordial non-Gaussianity in the CMB look for deviations from the bell curve distribution of temperature fluctuations. Standard inflation predicts nearly perfect Gaussian distributions, but some alternative models predict measurable deviations. Finding non-Gaussianity would revolutionize cosmology, potentially pointing to physics before or beyond inflation. The Simons Observatory in Chile is designed specifically to search for these subtle statistical signatures. The problem of initial conditions asks why the universe started in such a special state. The early universe had incredibly low entropy, uniform density, and flat geometry, all highly improbable conditions. The principle of indifference suggests we should expect typical rather than special initial conditions. This might mean our Big Bang was selected from a larger ensemble, perhaps through cosmological natural selection or anthropic selection in a multiverse. Observations of galaxy cluster collisions like the famous Bullet cluster reveal the behavior of dark matter through gravitational lensing. These cosmic crashes also test modifications to gravity that some propose as alternatives to dark matter. If gravity behaves differently than expected in these extreme conditions, it might hint at extra dimensions or other exotic physics that could connect to the universe's origin. The graceful exit problem plagued early inflation models. How does inflation end and transition to the hot Big Bang? This was solved by new inflation and chaotic inflation models, but the solution requires fine-tuning. Some cosmologists argue this fine-tuning points to deeper physics, perhaps initial conditions inherited from before inflation or selection effects in a multiverse. The way inflation ended might carry clues about how it began. quantum discord, quantum correlations beyond entanglement might survive cosmological transitions better than we thought. While entanglement is fragile, discord can persist in noisy environments. If our universe emerged from a quantum transition, discord from the previous epoch might survive, encoded in subtle correlations we haven't yet recognized. This could be a new window into pre-Big Bang physics. The coincidence problem asks why we happen to live at the special time when dark energy and matter density are comparable. For most of cosmic history, one or the other dominates overwhelmingly. Some solutions invoke anthropic selection, but others suggest we're not at a special time. Rather, the universe cycles through phases, and what we call the Big Bang was just one transition in an eternal cycle. The trans-Planckian censorship conjecture, proposed by Kumran-Vafa and others, suggests that quantum gravity effects prevent any physical process from probing distances smaller than the Planck length. If true, this would place fundamental limits on what we can learn about the Big Bang's earliest moments. The universe might have built-in privacy settings that hide its deepest origins. Yet this censorship itself might be the clue. Perhaps what we call the Big Bang is simply the boundary where quantum gravity effects become dominant, not a true beginning, but a horizon beyond which our current physics cannot see. Observations from the South Pole Telescope have revealed thousands of galaxy clusters through their shadows on the cosmic microwave background, the Sunyaev-Zeldovich effect. The distribution and evolution of these clusters test our models of structure formation. Some clusters appear too massive too early, suggesting either our understanding of dark matter is incomplete or that some structures might have origins predating our current cosmic epoch. These ancient clusters might be fossils from before the Big Bang. The dimensional reduction hypothesis suggests that at extremely high energies, the universe effectively has fewer dimensions. Near the Planck scale, space might transition from 3 dimensions to 2 or even 1. The Big Bang might have been a dimensional phase transition, where a lower dimensional precursor universe suddenly unfolded into our familiar 3-dimensional space. This would explain why the universe appears to have begun in such an ordered state. It inherited this order from a simpler, lower-dimensional predecessor. String gas cosmology proposes that the early universe was filled with a gas of fundamental strings at extremely high temperature. As the universe cooled, these strings would annihilate or expand, naturally explaining why only 3 spatial dimensions became large while others remained compact. The Big Bang wasn't the beginning, but rather the moment when our dimensions separated from the others. Evidence for this might be found in subtle violations of Lorentz invariance at high energies. The cosmic microwave background contains anomalies that challenge our standard models. The cold spot, spanning about 5 degrees of sky, is far larger and colder than typical fluctuations. Some propose it's evidence of a collision with another universe, a cosmic bruise from our bubble universe bumping into a neighbor. The axis of evil, large-scale alignments in the CMB, might indicate that our universe has a fundamental directionality inherited from its formation process. Pulsar timing arrays are becoming sensitive enough to detect gravitational waves from the early universe. The nanograv collaboration has found hints of a gravitational wave background that doesn't quite match predictions. This could be noise, or it could be our first detection of exotic physics from the universe's earliest moments, perhaps even from before what we call the Big Bang. The European Pulsar Timing Array and the Parkes Pulsar Timing Array are working to confirm these tantalizing hints. The universe's matter-antimatter asymmetry remains one of cosmology's greatest mysteries. For every billion antimatter particles in the early universe, there were 1,000,001 matter particles. That tiny excess is why we exist. Some theories place the origin of this asymmetry before the Big Bang, in the initial conditions or in physics that operated during a bounce or collision. The excess might be a fossil from a previous cosmic epoch where different physics operated. Loop quantum gravity predicts that at extremely high densities, quantum geometry effects cause space to become discrete. The big bounce emerges naturally. Gravity becomes repulsive at the Planck density, preventing singularities. But more intriguingly, some loop quantum gravity models predict that information from before the bounce survives in a scrambled form. We might be living in a universe that contains encrypted messages from its previous incarnation, written in a code we haven't yet learned to read. The de Sitter anti-de Sitter correspondence suggests our accelerating universe might be holographically dual to a conformal field theory. This duality could extend through the Big Bang, connecting our universe to whatever preceded it through a holographic relationship. The information of the previous universe wouldn't be destroyed but transformed, encoded on a different dimensional surface. The Big Bang might have been a holographic phase transition. Observations of fast radio bursts, mysterious millisecond pulses from distant galaxies, have revealed that the universe's electron density perfectly matches what's needed for these signals to reach us. This cosmic conspiracy might be anthropic selection, or it might hint at deeper organizing principles. If the universe's properties are fine-tuned for observation, perhaps observation itself plays a role in cosmic evolution, retroactively determining initial conditions through a kind of quantum-delayed choice on a universal scale. The Penrose-Hawking singularity theorems proved that under general relativity, singularities are inevitable given reasonable assumptions about matter and energy. But these theorems break down when quantum effects are included. Quantum gravity might naturally resolve singularities, replacing them with regular transitions. The Big Bang singularity might be a mathematical artifact of incomplete physics rather than a real physical event. Cosmic inflation, despite its successes, faces growing challenges. The measure problem, the trans-Planckian problem, and the initial conditions problem all suggest inflation might be incomplete or wrong. Alternative theories like Ekpyrotic cosmology, string gas cosmology, or conformal cyclic cosmology might better explain our universe's properties. The next decade of observations might revolutionize our understanding of the universe's earliest moments, or what came before them. The quantum eternity theorem, developed by Alexander Vilenkin, proves that inflation, once started, cannot have been past eternal. Using quantum mechanics and general relativity, Vilenkin showed that inflationary spacetimes must have a beginning. But this doesn't mean the Big Bang was the absolute beginning. It might have been preceded by a non-inflating quantum state, a contracting universe, or something even more exotic. The theorem tells us inflation had to start, but not what started it, or what came before. Recent observations from the Dark Energy Survey have mapped dark matter's distribution across billions of years of cosmic history. The maps reveal that dark matter forms a cosmic web that guides normal matter into galaxies and clusters. But some features of this web are puzzling, alignments and correlations that extend farther than expected. These might be remnants of pre-inflationary physics, structures that somehow survived the cosmic transition we call the Big Bang. The information paradox extends beyond black holes to cosmology itself. If information cannot be created or destroyed, then the information content of our universe must have existed before the Big Bang in some form. This information might have been compressed to the Planck scale, encrypted in quantum correlations, or stored in extra dimensions. The cosmic microwave background with its tiny fluctuations might be the universe's way of encoding its entire past history, including what came before. Studies of cosmic topology using the CMB have searched for repeating patterns that would indicate if space wraps around itself. While we haven't found clear evidence of a finite universe, we can only observe a limited region. The universe might be like the surface of a hypersphere or hypertorus, finite but unbounded. If so, the Big Bang might have been a topological transition, a change in how space connects to itself rather than a creation event. The emergence of classical reality from quantum mechanics remains mysterious. The universe began in a quantum state, but we observe classical galaxies and stars. This quantum to classical transition might hold clues about the Big Bang itself. Perhaps what we call the Big Bang was the moment when the universe's wave function first collapsed, when quantum superposition gave way to classical reality. Before that moment, the universe might have existed in an indefinite quantum superposition of all possible states. Gravitational memory effects, recently confirmed by LIGO, show that passing gravitational waves permanently displace test masses. The universe might carry gravitational memories of events before the Big Bang, permanent distortions in space-time that encode information about previous cosmic epochs. These memories would be incredibly subtle, but future gravitational wave detectors might be sensitive enough to detect them. The cosmic censorship hypothesis suggests that nature abhors naked singularities, infinities not hidden behind event horizons. If the Big Bang was a naked singularity, cosmic censorship might have required special initial conditions or connecting physics to resolve it. The universe's apparent fine-tuning might not be for life, but for mathematical consistency, ensuring that singularities remain properly clothed by horizons or resolved by quantum effects. Observations of ultra-diffuse galaxies, galaxies as large as the Milky Way but with only 1% of its stars, challenge our understanding of galaxy formation. These ghostly galaxies might have formed from different initial conditions than normal galaxies, possibly preserving information about variations in the early universe that standard inflation can't explain. They might be cosmic fossils from a time when the universe's physics was subtly different. The entanglement entropy of space-time itself might encode the universe's history. In theories where space-time emerges from quantum entanglement, the Big Bang might have been an entanglement phase transition. The universe before might have had different entanglement patterns, corresponding to different geometries or even different numbers of dimensions. Measuring entanglement entropy in cosmological observables might reveal echoes of this pre-geometric phase. The cosmic neutrino background, when finally detected, might reveal surprises. Neutrinos oscillate between different flavors as they travel, and this oscillation depends on their mass and energy. Primordial neutrinos have been traveling since the universe was 1 second old. Their flavor distribution might encode information about physics at temperatures of 10 billion Kelvin, possibly including phase transitions or symmetry breaking that preceded our current physics. Tests of CPT symmetry, the combination of charge conjugation, parity, and time reversal, at cosmological scales might reveal violations that explain the universe's matter-antimatter asymmetry. If CPT is violated, it might point to a fundamental arrow of time built into physics itself, potentially explaining why we observe a universe evolving from the Big Bang rather than toward it. The universe's directionality might be more fundamental than thermodynamics suggests. The nature of dark energy remains cosmology's deepest mystery. If dark energy is dynamical, changing over time, then it might have been different before the Big Bang or might trigger future transitions. The coincidence that we live when dark energy has recently begun dominating might not be coincidence but part of a larger cycle. Some models suggest dark energy might eventually decay, triggering a new Big Bang and resetting the cosmic clock. Analog cosmology experiments using Bose-Einstein condensates or other quantum systems are beginning to simulate cosmic phenomena in the laboratory. Researchers have created analog universes that undergo inflation, form horizons, and emit Hawking radiation. These experiments suggest that key features of cosmology might be emergent rather than fundamental. If universes can be simulated, perhaps our universe itself emerged from a simpler underlying reality. As we stand at the frontier of cosmological knowledge, the question what came before the Big Bang transforms from a philosophical musing into a scientific research program. The theories we've explored, eternal inflation, cyclic cosmologies, quantum bounces, Brane collisions, and holographic transitions, aren't just mathematical curiosities. They make testable predictions that the next generation of telescopes and experiments will investigate. We're living in the golden age of cosmology, where questions once thought unanswerable are yielding to human ingenuity and technological prowess. The Vera Rubin Observatory, beginning operations soon, will map billions of galaxies with unprecedented precision, potentially revealing patterns that echo from before the Big Bang. The square-kilometre array, when completed, will detect radio signals from the cosmic dark ages, probing epochs closer to whatever beginning our universe had. The Cosmic Microwave Background Stage 4 experiment will measure the CMB's polarization with sensitivity that might finally detect primordial gravitational waves or reveal the signatures of a cosmic bounce. Space-based gravitational wave detectors like LISA will open an entirely new window on the early universe. Unlike light, which couldn't travel freely until 380,000 years after the Big Bang, gravitational waves could propagate from the very first moments. LISA might detect waves from cosmic strings, domain walls, or phase transitions that occurred in the universe's first fraction of a second, or even from before what we call the beginning. The philosophical implications of these ideas transform our cosmic perspective. If the Big Bang wasn't the beginning, then our universe becomes part of a larger story, perhaps an eternal story with no beginning or end. We're not living in the aftermath of a unique creation event, but in one chapter of an ongoing cosmic novel. The atoms in your body might have existed not just in previous stars, but in previous universes, recycled through cosmic cycles beyond imagining. This perspective doesn't diminish the Big Bang's importance, it magnifies it. The Big Bang becomes not just the birth of space and time, but a cosmic transformation, a gateway between different phases of eternal existence. It's the event that set the stage for galaxies, stars, planets, and ultimately consciousness to emerge in this particular cosmic epoch. Whatever preceded it, the Big Bang marks the beginning of conditions that allowed our existence. The multiverse, in its various forms, radically expands our conception of reality. Whether it's the quilted multiverse of regions beyond our horizon, the inflationary multiverse of eternal bubble creation, the quantum multiverse of parallel branches, or the mathematical multiverse of all possible structures, we're forced to confront the possibility that our universe is not unique. This might seem to diminish our cosmic significance, but it actually enhances the preciousness of our particular corner of reality. Consider what these ideas mean for the ultimate fate of our universe. If cosmic cycles are real, then the heat death predicted by standard cosmology isn't the end, but a transition. The universe might phoenix-like recreate itself from its own ashes. If eternal inflation is correct, then even as our universe ages and cools, new universes are constantly being born elsewhere. Reality itself might be eternally creative, always finding new ways to exist and explore possibilities. The anthropic principle takes on new depth in this context. We observe a universe suitable for our existence not because it was designed for us, but because we could only exist in such a universe. In the vast ensemble of all possible universes, whether separated by space, time, or quantum branches, observers naturally find themselves in regions compatible with their existence. Our universe's apparent fine-tuning becomes a selection effect rather than a mystery requiring explanation. Yet mysteries remain, perhaps deeper than ever. Why does anything exist at all? Why these laws of physics and not others? Why is there something rather than nothing? These questions might push beyond science into philosophy and metaphysics, or they might yield to future insights we can't yet imagine. The history of science is filled with seemingly unanswerable questions that eventually yielded to new ways of thinking. As we reflect on these cosmic possibilities, remember that you are part of this grand story. The calcium in your bones, the iron in your blood, the carbon in your DNA, all were forged in the nuclear furnaces of dying stars. But more than that, the very particles that compose you might have existed in previous cosmic epochs, survived universe-ending transitions, and emerged into our current reality. You are not just in the universe, you are the universe, organized temporarily into a form capable of contemplating its own existence. The quest to understand what came before the Big Bang is ultimately a quest to understand ourselves and our place in existence. Whether the answer is eternal inflation, cyclic cosmologies, or something we haven't yet imagined, the search itself transforms us. It connects us to the grandest scales of reality while reminding us of our cosmic heritage. Every time we look up at the stars, we're not just seeing distant suns, we're seeing family, seeing home, seeing echoes of whatever immortal process gave birth to it all. This is the gift of modern cosmology, the knowledge that we live in a universe far grander, far stranger, and far more wonderful than our ancestors imagined. The Big Bang might not have been the beginning, but it was the beginning of the conditions that allowed atoms to form, stars to shine, and consciousness to emerge. In that sense, it remains the most important event in our cosmic story, the transformation that made our existence possible. As you go forward from this exploration, carry with you the wonder of these possibilities. When you see the night sky, remember that you might be looking at just one universe among infinities, one moment in an eternal cosmic dance, one bubble in an endless champagne of creation. Yet this makes our universe not less special, but more so. In all the vast possibilities of existence, here is one that created beings capable of love, wonder, and the curiosity to ask where it all came from. If you made it this far, make sure to subscribe to the channel and give a thumbs up. Your support means a lot to me, and if you enjoyed this video, I am sure you will love this other one at the left side of the screen, Journey to the Center of the Milky Way. In this epic space documentary, we embark on a virtual journey across 26,000 light-years, from our solar system, through star clusters, nebulae and cosmic clouds, all the way to the supermassive black hole at the heart of our galaxy. See you there.